Hello and welcome to Vector Calculus with Sal. In this episode, we'll talk about vector line integrals. Consider the spring mass system. Now, the force that a spring applies to a mass is given by minus a spring constant K times X for a one-dimensional spring mass system. But if we had a three-dimensional spring mass system, we'll have to use a vector. This could also be written as minus K times R to generalize the one-dimensional example. Here's our force vector field for a 3D spring mass system. Notice two key features. One, that the vectors always point back towards the origin. That makes sense. There's always a restorative force that pulls back the mass towards the origin where the spring is attached. The second key feature is that the farther away we get from the origin, the larger the restorative force is. That makes sense, since the more we stretch the spring, the more the spring will apply a stronger restorative force. Now consider the following trajectory that a mass could take in this 3D spring mass system. Here I'm labeling the x-axis, the y-axis, and the z-axis is coming out of the page. So let's take our spring mass system, set the mass and spring constant equal to 1, the initial position along the x-axis at x equals 2, and nudge this in the direction of positive y with initial speed of 1 meter per second. What we get is this elliptical motion on the xy plane. Let's see the amount of work that the spring does on the mass as it's going around this elliptical orbit from the positive x-axis to the positive y-axis. The mass starts at x equals 2 on the x-axis and swings in an elliptical orbit to y equals 1 on the y-axis. We would like to know the amount of work that this spring does on the mass as it's swinging in this elliptical orbit. We know that the work is equal to the force times the displacement. But force is a vector and so is displacement. So this multiplication is actually the dot product between these two vectors. So what can we put in for force and displacement? Well, this trajectory is elliptical, and it's not at a constant distance away from the origin. So this r will vary in magnitude, and hence so will the force. The force is not constant along this trajectory. And the angle that it makes with the displacement is also not constant. So we can't just put any good old force vector in any simple displacement in our equation. What can we do in this situation? Well, why don't we apply the trick of breaking up our trajectory into very small segments of motion. Let's also consider position vectors, one that points at the initial point of one of these small segments, and another that points at the end of one of these small segments. Let's now zoom in into one of these small segments. And let's also take a look at our force vector as we move along this small trajectory. Here the mass is being pulled straight back towards the origin, as we would expect from this type of force vector field. Now we've chopped up our trajectory into such small pieces that roughly the force at the beginning of the trajectory is the same as at the end of the trajectory. Let's just draw it as F coming out of the middle. At this point, star. Let's also look at the displacement around this small piece of this trajectory. We have that delta R is equal to R2 minus R1. Hence, it points along this way. So, because the force is roughly constant through this very small piece of the trajectory, we can just consider the force at any one of the points in this small segment as equal to all of the points of this very small segment. And the smaller our segments, the more accurate this approximation. So the small amount of work that'll be done just through this small segment is going to be equal to F star dot delta R for just a small segment delta R. So that should give us the work done for just that small segment. Well, how do we consider all segments? Here, we're going to need a parameterization. Let's track our motion using this time parameter. So at time equal to t naught, we'll be at the initial position at r naught. This is where t equals t naught. And t final will correspond to the final position. And we'll get position vectors everywhere in between as we move along this trajectory. Thus, our parameterization is the vector valued function r of t, which maps our time axis to our position. This is called a parameterization, and the bounds of our time will be t naught and tf. So let's now return back to our work formula for the small segment. So the small amount of work done in one of these tiny segments is going to equal F star, the force when we're traveling through that segment, dot delta R, which is the change in position vector throughout that segment, also called the displacement. But we're now tracking our trajectory with time. So we can substitute for F star the position at t equals t star when we're at that small segment we've been zooming in on and considering. And we can then dot it with delta R over delta t times delta t. This looks like a trivial substitution since you could divide out the delta t's, but it'll allow us to use velocity instead of our positions. And this will help us since, again, we're tracking with time. Now, let's break our segments into the smallest pieces. In other words, let's take the limit as delta t goes to 0. What do we get then? We'll get that dw, instead of a delta now d, is equal to f of r when t is t star, when that is the time when we reach our small segment, dot delta r over delta t as delta t goes to 0 is the derivative of r. Hence, we'll get the velocity times a small time. Since the segment is small enough, this formula works really well and is extremely accurate. So why don't we add up all the pieces of work that we do for these small segments? Why don't we take the integral? Thus, the total work will be equal to this formula on the right. This is the formula for our vector line integral, and let's write it one more time in polished form. So the work, which is a vector line integral, is equal to the integral of f dot small displacements dr around a certain curve, and we've just derived that formula if we parameterize with time. Let's now use this formula to compute the work that the spring does on the mass as it follows the trajectory from the x-axis to the y-axis in this elliptical path. So the first ingredient that we should consider for computing vector line integrals is the parameterization. In order to obtain the parameterization for our curve, notice that our curve is moving counterclockwise with a semi-major axis of 2 along the x-axis and a semi-minor of 1. Why don't we try this format for elliptical curves? Some constant a times cosine t, this will be for the semi-major axis in this ellipse, the a constant, b times sine of t, and nothing's really going on the z-axis, so 0 for z. To fill the constants a and b, we'll make substitutions for 2 for the x-axis because we're starting at the x-axis at 2, and 1 along the y-axis for our semi-minor axis. Thus, so far we have an elliptical curve with semi-major axis along the x-axis and equal to 2, and some semi-minor axis length on the y-axis equal to 1, and nothing happening at z. But we're still not done. We need the bounds of our parameterization, and that's found with 0t less than pi over 2. This will start us along the positive x-axis and end along the positive y-axis. Here then is the parameterization that we sought. So in part 2 of this episode, we got our parameterization. And in this part, we'll get our second ingredient, which is the velocity. Now, computing the velocity is just taking the derivative of our parameterization. Hence, we'll get negative 2 sine t cosine t 0. This then is our second ingredient. So our first ingredient was the parameterization, our second ingredient was the velocity, and now our third ingredient will be plugging in the parameterization into our vector field. Now our vector field is f is equal to minus k x y z. In fact, we've chosen k to equal 1. There was no mathematical reason to do that. We just set all of the constants in this example to 1 in order to deal with a purely mathematical problem. Hence, our vector field is actually equal to minus xyz. How do you plug in the parameterization? Well, f of r of t is equal to minus x of t. So wherever we saw x, we put x of t. Wherever we see a y, we put y of t. And wherever we see a z, we put z of t. What then do we plug in for our x of t, y of t, and z of t? Well, these come from the parameterization. So we'll plug in for x of t, the x component of our parameterization, y of t, the y component, and z of t, the z component. We now have our third ingredient, which is plugging in the parameterization into the vector field. So don't forget, we're tracking this trajectory with time. And what you're seeing there is what the vector field value would be at a certain point, which corresponds to a certain t time on our clock. So our first ingredient was the parameterization, the second the velocity, and our third ingredient, which we found in the last part of this episode, is plugging in the parameterization. In this part, we'll get the fourth ingredient, which is taking the dot product to find the integrand. The integrand is f of r of t dot the small displacements. That will equal f of r of t. And the small displacements, we've computed a formula for that. It's the velocity times the small change in time. Well, we just take our plugged in parameterization, put it in here, and we take the velocity and put it in here, and compute the dot product. Then the above term will equal our f of r of t, which is negative 2 cosine t minus sine t 0 dot our velocity, r prime of t, which is negative 2 sine t cosine t 0 times dt. To compute the dot product, you sum the first component of the first vector times the first component of the second vector plus the second component of the first vector times the second component of the second vector plus the third components multiplied. And simplifying, we'll use the trig identity, and thus our integrand will be equal to 3/2 sine 2t dt. Thus, in the previous parts, we found our different ingredients. 1 was the parameterization, 2 was the velocity, 3 plugging in the parameterization into our vector field, and 4 taking the dot product to get the integrand. We found the integrand to be equal to 3/2 sine of 2t. In this part, we'll put it all together in our formula. So going back to our formula for the work, we have that work is equal to this vector line integral over our curve. We'll get the bounds of our integral from the bounds of our parameterization. We'll get our integrand from the dot product, and we'll compute this simple Calc2 integral now. Let's conclude with some key insights into this problem. One is that the curl of our vector field hence the curl is identically 0. That's our first key insight. Our second insight is that f can be written as the gradient of some scalar function if we would choose that phi is equal to negative 1/2 x squared plus y squared plus z squared. Our third key insight was that this vector line integral, the only thing that mattered were the actual beginning points and end points. So if we take phi and plug in, so all that mattered were the beginning points and end points for actually computing this integral if we would use our scalar function phi. Our last insight is to realize that if all that matters is the beginning and end point, what if we chose the same point for the beginning and end point? So let's take a simple curve, a simple closed curve with the same beginning and end point, and we should have found that it's equal to 0. So the work done around any closed simple path should be equal to 0. As we'll see in a later episode, this means that F is conservative, and thus if our force is equal to this term, which may also be written as minus kr, then phi will be equal to 1/2 k x squared plus y squared plus z squared minus that, which also may be written as minus 1/2 kr squared. Do these terms look familiar? Well, if you've ever studied the spring mass system in physics, you'll notice that our potential function looks a lot like the potential energy term in physics. And so does our force term if we generalize from one variable of x to r. This is all not a coincidence.